In this lecture, we are going to study about antiferro and ferrimagnetic materials. This is Unit 5, Lecture 7. First, we shall see what is antiferromagnetism. Antiferromagnetism arises in materials in which the magnetic moments are equal, but adjacent magnetic moments point in opposite directions. An antiferromagnetic unit cell can be considered as composed of two interpenetrating ferromagnetic sublattices, say A and B, as shown in the figure. The spin of A and B are oriented in opposite directions. As you would see, A, the spins are in up direction, whereas B, the spins are in downward direction. They are equal in magnitudes but opposite in directions. When there is no external magnetic field acting on them, the net magnetization is zero. When placed in an external magnetic field and the temperature is zero, the magnetization is still zero. As temperature is increased in the presence of external magnetic field, the antiparallel arrangement of spin is slowly disturbed and magnetization increases. So when magnetization increases, the susceptibility will also increase. The susceptibility reaches a maximum at a temperature called as Néel temperature. At Néel temperature, the spin ordering is lost completely. So this graph over here shows susceptibility versus temperature. So we can see as temperature increases, susceptibility also increases, reaches a maximum and then decreases. This point where the susceptibility is maximum is known as the Néel temperature. The susceptibility decreases with further increase in temperature and the material becomes paramagnetic above the Néel temperature. So above here it is paramagnetic in nature. The elements manganese and chromium exhibit ferromagnetism at a room temperature. Most of the antiferromagnetic materials are compounds. Example is MnO. Now we will see what is ferrimagnetism. In certain crystals, the magnetic moments of the two sublattices are not exactly equal in magnitude and they are oriented in opposite directions. They have a resultant magnetic moment. So though they are in opposite directions, magnitudes are not the same. So they will have some value of magnetization. They possess spontaneous magnetization. Ferrimagnetic materials are very similar to ferromagnetic materials in their macroscopic magnetic characteristics. Ferrimagnetic materials are widely used in high frequency applications where ferromagnetic materials cannot be utilized. We will see what is ferrites now. Ferrimagnetic materials are ceramic materials and are therefore good electrical insulators. The most important group of these materials is ferrites. Garnets constitute another important group. Ferrites consist of ferric oxide, that is Fe2O3, combined with one or more oxides of divalent metals. They are represented by a general formula MFe2O4 or MoFe2O3, in which M represents a metallic element. Example of ferrite is magnetite, which is given as FeO into Fe2O3. Garnets have a very complicated crystal structure and the general formula is M3Fe5O12, where M represents a rare earth ion such as samarium, yttrium, etc. Now what are the applications of these ferrites? They are used to produce ultrasonic frequency by magnetization principle. Ferrites are used in audio and video transformers. Ferrite rods are used in radio receivers to increase the sensitivity. Ferrites are used in computers and data processing circuits. Ferrites are also used in switching circuits and in storage devices of computers. So you have seen the difference between antiferro and ferrimagnetic materials in this particular